right, guys. And get started here. Make sure we're all good. Yep, okay. All right, so we're moving on from power cycles, and we are moving on to our last cycle section, which is awesome if you're so tired of cycles. So just a little bit longer, and then we're going to move on to something a little bit different. But vapor compression refrigeration slash heat pump cycles. So before we actually go on to those, I do want to kind of like bring you back a little bit to just what a refrigeration or a heat pump cycle is. So in Thermo 1, you analyzed it as a black box, just like we analyze power cycles as a black box. We did like a little backwards counterclockwise arrow. You had a high temperature reservoir, low temperature reservoir, and the whole point of it was not to generate work, but to transfer heat in the direction that it doesn't want to go. It doesn't want to naturally flow from what's colder to what's hotter. So I don't know why I'm putting an equal sign there. And transfer some of that energy. And then there may be a power input. Oftentimes there is not a power output. We will talk about the case that we do. So that W dot out is, I'll say it's not equal to 0. What's called a reversed Brayton or a gas refrigeration cycle. But for the vapor compression refrigeration cycle that we'll talk about now, and then we'll also talk about some sort of modifications or variations on that vapor compression refrigeration cycle, you will not have a power output, just a power input. So going back over here again, for refrigerator or refrigeration cycle, this could be a little bit smaller. This is space, right? It could be the refrigerated compartment. It could be your cooled house, right? And that high temperature reservoir, that thermal reservoir, that's the ambient. So that could be the kitchen that your refrigerator is sitting in. It could be the hot outdoors during the summer. If this is being run as a heat pump, so for a refrigerator, for all intensive purposes, these are doing the exact same thing. We're just going to call it something different based on what we're ultimately after. So for what we're going to call a refrigeration cycle, or a refrigerator, or an air conditioning cycle, we're interested in cooling a space. If we're going to call it a heat pump, we're interested in, am I keeping on that up? It's a heat pump. This class, we're going to call it a heat pump if we're interested in heating a space. So if it's a heat pump, this is our space. And that low temperature reservoir, if it's a heat pump, maybe that's the cold outdoors. Pulling heat out of the cold outdoors, and we're adding that thermal energy to our heated space, to our house. So that's, in a nutshell, very basic, what a refrigeration heat pump cycle is. And like I said, in Thermo 1, we didn't really care about what went on in that box, how that was accomplished. But here in Thermo 2, we do. So what you see in the top right hand corner, that is what's going on in that little box. So you have a refrigerant, right? It is a refrigerant, right? It's not water. It's going to be ammonia or something with an R in front of it, R22, something like that. You'll see propane can be used as a refrigerant. And so we have thermodynamic tables for various refrigerants, and they're read just like the tables for water. So if you look at this TS diagram, you can see from 1 to 2, you've got a compression process, and ideally it would be an isentropic process. From 2 to 3, this is the heat exchanger through which you're transferring that heat. So let's say that this is a refrigeration cycle. It's acting as a refrigerator. Well, at this point, from 1 to 2, your pressure is going up because you're compressing it, but also as you're compressing it and the pressure is going up, the temperature is going up as well. And so the temperature at state 2 is going to be higher than the temperature of that high temperature reservoir. Right? And as long as it's higher than that high temperature reservoir, heat's going to naturally flow from what's hotter, which is the refrigerant, your high temperature reservoir, which is at a slightly lower temperature. Once it transfers its heat, the temperature comes down. This is a constant pressure process. So you can see, this takes place along a line of constant pressure from 2 to 3. And then coming out at state 3, typically in this class, you'll see it come out as saturated, but it doesn't necessarily have to be. It could be subcooled. And then from 3 to 4, this is an isenthalpic, meaning the H value is constant, isenthalpic throttling process, right? So the processes here are they sort of mirror that Rankine cycle, right? You had isentropic compression, you had a constant pressure heat transfer process, then you had an expansion process. But here, of course, instead of in a turbine, right, because my refrigerator doesn't have a turbine in it, right, that expansion process is just accomplished with an isenthalpic throttling valve. And by that time, if you look at state 4 on that TS diagram, your pressure is dropped in that throttling process, and so your temperature has dropped as well. And so your T4 at this point is lower than the temperature in that low temperature reservoir, and so heat's going to flow from what's hotter, which is low temperature reservoir, to what's colder, which is your refrigerant. And then the cycle repeats itself. So if you do need some, kind of a review, there's some videos on thermodynamic cycles in general, and then there's also pretty much everything else. If you got it for the last unit, should be good. But if you need to review maybe a little bit, maybe this would be a good one to look back at. Okie dokie. There's another practice problem kind of referenced on here if you on a simple vapor compression refrigeration cycle. All right, so problem 1 here, we've got R22 enters the compressor of an ideal vapor compression refrigeration system as a saturated vapor. Saturated vapor at negative 40 degrees Celsius and a volumetric flow rate. That should say 15, shouldn't it? Not 14. So let's fix that. Is that what I calculated it with? Yeah, it should be 15. A typo on my part. 15 meters cubed per minute. The refrigerant leaves the condenser, and that's, it doesn't call it a condenser on my diagram here, but that's what it is, because if you look at that TS diagram, you'd see that at state 2, it's going to be coming in superheated, and then it's going to condense all the way to either a saturated liquid or a compressed liquid. And it looks like at state 3, this is probably a compressed liquid. But we will see in just a second. Condenser should be condenser. And then conversely, this one is an evaporator. Right? determine the compressor power. So that's going to be occurring between 1 and 2. This is my W dot N. And then we also want to find the refrigerating capacity. So the refrigerating capacity is the rate at which you pull heat out of that low temperature reservoir. So if you kind of want to think about it, this is your low temperature reservoir. And this is your dot L. Your high temperature reservoir, you're dumping heat. In a heat pump cycle, we would call that Q dot H the heating capacity, because it's the rate at which you're heating thing that you're interested in heating. But this is a refrigeration system, and so this right here is just your refrigerated space. Okay, and then we also want to find the COP. So COP is another one of those terms that's covered in that Unit 1 Thermo 1 Unit 4 video on this one right here, video 4.3 on refrigeration and heat pump cycles, but we'll go over it again in just a second as we get our governing equations. So we're going to say it's an ideal cycle. We're not given any indication that that compression process is anything but isentropic. No heat transfer where unintended, no pressure drops where we don't want them to occur. So across that heat exchanger from 2 to 3 and 4 to 1, we don't have a pressure drop. And 2, 3. Perfect. All right. So first of all, with these assumptions right here, steady state, kinetic, potential energy changes are negligible, your first law, in general, it's going to be dot in minus dot out minus W dot out minus W dot in. Oops. I have to scoot this over. Some of the M dot H's, and actually this is going out, minus the sum of the M dot H's going in. So that's our general form of the first law that we'll sort of reference. And so when I apply my first law to my compressor over here, I can get my value for W dot N. So for my compressor, you can see that cancel all this stuff out. I'll have W dot N is equal to the stuff going out minus the stuff going in. So here, this is going to be M dot times H2 minus H1. And it's just one little loop, so we don't have, split flows to keep track of. Like, we don't have to, pay attention where, mass flow rates change. No, it's the same. 1, 2, 3, 4, they're all the same. So the only thing, probably got to get this guy. So I know my mass flow rate. I can calculate that based off of my volumetric flow rate at state 1. So that's 15 meters cubed per minute. I will need to get V1, and I also need to get 1 and H2. So state 1, my two independent intensive properties. I've got my quality, it's 1, and and of course my temperature, I know him too. T1 is negative 3 degrees Celsius. And then what I'm going to use for H2, well, I know what the pressure is. The pressure is 9 bar. So P2 equals 9 bar. And then since it's an ideally isentropic process, S2 and S1 are equal to one another. So I'll probably need to get that as well. So I need to go to the tables for R22. So I'm going to go do that now. And instead of trying to flip around and see where these are, you might want to go to your table of contents here to figure out where it is. So we are SI units, right? Yes, this will be saved on the unit 3 playlist. All right, so this is an SI unit, so R22. Yeah. Right here where we're going. So I'm going to go to page 51. There we go. So -40 is state 1. That's this guy right here, and so actually I don't like that color. Something we can actually see. There we go. All right. So it's a saturated vapor. So there's my S value, and there's my H value. I'm good there. Let me go ahead and go write those down. So my H value, 233.27. And my S1 value is 1, and then there's 3 zeros and a 5, and it's kilojoules. Bam. So now we need to figure out what phase state 2 is, and it's kind of obvious, right? If I think about what's going on in a TS diagram, state 1, right on that saturated vapor line, press it isentropically, only one place to go, and that's into that superheated region. Now you can verify that it is. Let's pretend like that we have. We go do verify. Well, might as well. We're right here. Yeah, you can see my saturated tables organized by pressure. Here at 9 bar, you'd have to be at a temperature of, or I'm sorry, you have to have an enthalpy of 0.9001 or less, or between 0.2591 and 0.9001, and we're at 1.005. So clearly it's superheated. So I need to go find the box that corresponds to 9 bar. Hopefully we have one. Perfect. Perfect. So I'm going to kind of zoom out. This is table A9. And wait, is it 1.00? Actually over here, isn't it? That one. It's going to be somewhere in there. So this is, again, 11, A9. So this is A9. This is temperature, specific volume, internal energy, enthalpy, and entropy. And we have a value of 1.0005. And so clearly your enthalpy is going to be between 280 and change and 288 and change. And so I've got a value of 287.55. 287.55 per kilogram. And it just occurs to me that there's probably another property that I should have pulled off at V1. So this is in table A9. This is in table A7. But I do have a specific volume. Let me go ahead and get that. 0.2052 cube kilogram. All right, and so at this point, it really is, it's plug and chug. There's not going to be any unit conversions for me to worry about. I do have a W.N, should get it in kilojoules per second, which is kilowatts. And I've got a value of 66.13. That's kilowatt. Okay, perfect. That's my W dot N. I got to figure out what Q dot L. So that Q dot L is a Q dot N to my system. It's a Q dot N in between 1 and 4. So I'm going to cancel out all these guys, and I'm going to see it's the stuff going in minus the stuff. Actually, wait a minute. I'm sorry. Stuff going out minus stuff going in. Sorry about that. So this is going to be M dot times, let's see, it's going to be H1 minus H4. So, I've sort of started making my way around the cycle. I had H1, H2, and then of course between 3 and 4, this is the throttling process, so H4 and H3 are approximately the same. And so let's go ahead and that guy. So H4 approximately equal to H3, which is going to be at 9 bar and 19 degrees Celsius. So I'm going to go look at my saturated tables. I'm going to go and look in the ones organized by temperature. I could look at the ones organized by pressure, but I'm going to go with the ones organized by temperature, and I'll show you why in just a hot second. So A7. So we are at 19. That's too bad that it's not right on there, but it's okay, I guess. This is gonna be, oh wait. Oh, it's 19. There, not though. No. Fine. Try to make it so we can see everything. Doing my best here. Let's see, it's gonna be somewhere on that line right there. Okay. So 19 degrees Celsius and 9 bar. So probably first thing I need to do is actually, instead of interpolating, let's go show it does end up being compressed. Maybe I could go over here. So at 9 bar, you can see that if it was going to be saturated, the temperature would have to be 19.59 degrees Celsius. So it is slightly compressed. So I will kind of make a note. Oh, it's compressed. And you'll see that you do not have compressed liquid tables for R22, and you don't really have compressed liquid tables for any of those refrigerants. And so we're going to use a compressed liquid approximation, which would be that it's going to be approximately equal to H sub F at whatever the temperature is. So our temperature is 19. Just want to zoom in. There. So this is our H sub F column. So you can see the H sub F at 19 degrees Celsius is going to be between 64.19 and 69.09. At a value of 67. Yeah, that looks okay. 67.87. So 7.87 is what you've got. And I'm going to write that on my notes, but I just want to show you where that came from. So this is approximately H sub F, 19 degrees Celsius, which is 67.87. That's kilograms per kilogram. All right. And at this point, you should have already, been able to plug in and get that M dot. If you want a value for it, I do get one. It's 73.10. I've got it in kilograms per minute just because that V dot was in 15 meters cubed per minute, so per minute. But you can easily convert that to seconds. So I have a dot L of, oh man, I want it in tons. Okay, fine. That's fine. So I'm going to have, actually, let's, I guess, bring this down just a tiny bit. There we go. So this is going to 73. It's going to be 73.10 kilograms per. Our H1 was 2.327 kilojoules per kilogram minus H4, which is 67.87 kilojoules per kilogram. See that this is going to give us kilojoules per minute, and the conversion factor, and if you look on your conversion factor sheet, let's go there together just to make sure that we've got it. 2, 5, I guess. So ton of refrigeration, there we go. It's right there. So a ton of refrigeration is 200 BTU per minute, or 211 kilojoules per minute. So go do that. There we go. 1 ton of refrigeration, 211 kilojoules per minute. There's my conversion factor. I end up getting 7 tons. Right. And then for part, the box, the other one in black, I guess. Otherwise. All right, so then the next thing that we need to do, very last thing we need to do for this guy is our coefficient of performance. So our COP, and it's for a refrigeration cycle. So for a refrigeration cycle, it's what you're interested in over what you have to put into it. So what you have to put into it is your W dot net. So that means any W dot in minus any W dot out. Of course, we don't have any W dot out for this particular cycle, so it's just going to be W dot in over what you're interested in. And what you're interested in is filling your space, so it's dot L. If it were a heat pump, it'd be the exact same equation, except on the numerator, you'd have a Q dot H, because that's what you're interested in. All right, so we have, I'm going to go ahead and put this, this guy is M dot times H1 minus H4. And then our equation up on the top for W dot N was H2 minus H1. And then cancel out those M dots. And so I won't have any unit conversions to do. I've just got the enthalpy values, and I've got all of those values. And this ends up being 3.05. So it's a number. It's not a percentage or anything like that. It's just a number. Sometimes you'll see this written as beta. I think that's the way that your book writes it. I'm in the habit of just writing COP subscript R, but either one is fine. Right, so we have a vapor compression refrigeration cycle, operates at steady state with refrigerant R134A as the working fluid. Oh my god, I'm sorry. Sorry, oh my goodness. All right. Saturated vapor enters the compressor at 2 bar, and saturated liquid, which is at state 3, exits the condenser at 8 bar. All right. Isentropic isentropic efficiency of our compressor is 80%, and they point blank give us the mass flow rate. So pretty much everything that we calculate here, it's pretty much the exact same thing. It's easier in one respect because I don't have to calculate the m dot. So I guess the only thing that makes it a little yucky is just the fact that we have an isentropic efficiency that we have to worry about. But that, everything's good. Hey, write all my stuff here. So this one is super easy, so we're gonna go over it really quick. Um, so oopsies. The only thing that I'm seeing in my assumptions is a copy paste mistake on my part because the isentropic compressor doesn't have an efficiency of 100%, but everything else is fine. All right, so governing equations. So I'll put this as A, B, C. And it is the exact same thing as the previous problem. W dot n, it's going to be m dot times h2 minus h1. Your Q dot L, which is of course in tons. I do have some unit conversions to worry about there, but it's fine. H1 minus H4. And your coefficient of performance, what's that being? So it's what you're interested in, which is your Q dot L, H1 minus H4 times M dot, which is going to get canceled out or divided out over what you have to put into it, which is your W dot net N. In this case, it's only a W dot N. So this right there, that's the majority of your points on a test. Because I know it's super annoying to have to figure out, looking at tables and get all those H values. That's where most of your points are going to go, and that I would have gotten that in 5 minutes, and then had the rest of my time to get my H values. So, okay. So let's go get our H values. All of our states. So H1. Actually, I'm going to make this state. So state 1, we got H, and we've got what? Pressure, I think. Vapor 2 bar, yep. So we've got P1. 2 bar, sorry. Bar. Got a saturated vapor. Go ahead and get our S value. And I'm just sort of gonna put a placeholder here just so I could sort of walk all through. State 2. State 2, you're gonna have a state 2S, and then you'll have a state 2. So your state 2S is gonna be where your entropy at 8 bar has an entropy. State 2S and state 1 is the same. And then of course to get actual H2 value, you need to use the equation for that isentropic efficiency. So ideally you wouldn't have to put a lot of work into it, so it's going to be on the top, and the actual work you need to put in it is H2 minus H1. I got that. Let's get state 3. State 4 shouldn't be bad at all because found state 4, or if you found state 3, you found state 4, right? And it looks like we've got a quality and we've got a pressure at state 3, so we're all good there. So this is going to be H with a quality of 0 and a pressure of bar. Ta-da. All right. So now I've got sort of a placeholder for everything, and I'm ready to get my governing equations. So, or not my governing equations, but all my states. So state one, we need to look in table A 134, or the table for A 134. So let's see. It's like that one, this one. So yeah, these guys, yeah, 57, 58, 59. So state one, we're at 2 bar, so I need to go to A11. Go. So 2 bar. And going into that compressor, you're going in, oopsies, as a saturated vapor. So there's your quality. There's your entropy. Go ahead and write that. So 2.3. And then your entropy is 0.9253. 0.9253 kilojoules per kilogram K. Over here, if it's at 8 bar and you've got an entropy of 0.9253, you know, it means you sort of think back to what that TS diagram looks like, because you know that if you're going in at state 1 as a saturated vapor and you're compressing, you uploading the missing content of unit 1 and 2 for term 1. No. Yeah. Yeah, anything that's on the Unit 1 playlist or Unit 2 playlist, that is what it is. Yeah, everything else is covered in lecture, which is in person. Okay. So, all right, so it is superheated. So I do need to go to those superheated tables. And I guess, let's see, 8 bar is where I'm going. Perfect. Right. So we are at 8 bar and our entropy is 0.9253. 253. So it looks like we're going to be in between these guys right here. So your entropy should be between 264 and change and 273 and change, and I've got 269.92. So 269.12. All right. Of course, with this guy, in 80%, I can solve for my H2, and my H2 ends up being 277.08. Right. Easy peasy, right? So for state 3, you've got saturated liquid, 8 bar, so you do need to go to those saturated tables. So this is going to be, here we go. So A11, you're at 8 bar. Of course, we are saturated vapor. So your H value is going to be 93.42. Right, 93.42. This is kilogram. Right. So at this point, you know, the only other thing to do, I mean, coefficient of performance, you're not going to need any unit conversions whatsoever because, well, those units are just going to work out, aren't they? But go ahead and plug this in. So this ends up being 4.13. Your W dot N, as well, throw some numbers in here. So this is going to be 7 kilograms per second. Let me just smaller. 7 kilograms per, actually 7 kilograms per minute. 1 minute, 60 seconds, because I want things to be in kilowatts. And then H2 minus H1, 277 point minus 2, 1.3. And that would give me things in kilowatts or kilojoules per second. So I've got a 4.17 kilojoules per second or kilowatts. So that's that guy. The only other thing I need to do is I just need to make sure that get things in terms of tons of refrigeration. Yeah. So it's going to be 1 point minus my H4, which is 93.42. That's kilojoules per kilogram. And my unit conversion that I'm going to be using, 1 ton of refrigeration is 211 kilojoules per minute. And I think that work itself out, and I've got 4.906 tons refrigeration. Okay. So the very next section, and we won't start that today just because it's a whole nother section, but I will sort of like introduce the concept with the hopes that you will watch video 3.2. So a cascade refrigeration cycle, it is basically just 2 vapor compression refrigeration cycles sitting on top of one another. And it allows you to use different refrigerants to better suit the pressure, the operating pressures that you are going to be using. So yeah, in general, you want to avoid very low pressures, very high pressures. And so this will, you know, by sort of putting 2 together, you can achieve very low temperatures in that low temperature reservoir, and avoid those excessive pressures. So I will leave it up to you to make sure that you do watch the video 3.2, and then when we come in on Wednesday, we will go ahead and solve problem 3, okay? All right, well, if you have questions, I will, let's see, I forget. I don't think you guys actually, I'm not mistaken, I don't think you guys have, I don't think there are office hours for Thermo 2 typically on Tuesdays. Let's see. Yeah, if you haven't, if you don't know, show you. So there's a, maybe it's Thursdays, I guess, that we don't have office hours, but there are quite a lot of office hours. So, you know, if you're struggling, make sure that you do take advantage of that. There are also, if none of those work for you, or if you don't particularly like me or the TA, it's okay. There is tutoring for Thermo 2 available through the, I don't know, through the tutoring center. So this is not something that's controlled by me. They don't have drop-in office hour, or they don't have drop-in times, but they do have someone that is, they're paying to be there and tutor for that. So all you have to do is make an appointment. They don't always have it for Thermo 2, so this is something a little bit, you know, I was surprised to see it. So if you need it, take advantage of it. Okay. Righty. It's a unit of energy. Yes, the ton is a unit of energy removal. Yeah, so it's tons of refrigeration as opposed to like a unit of mass. Yeah. Okay. So how about this? I will kind of turn off my screen so it doesn't look like I'm staring at you, but I'll just sit here till 2:15, and that way if you do have questions, you just pipe up, okay? All right. Thank you guys. Appreciate it. Thank you. Thank you.